Hey everyone, welcome back. So in this video, there's quite a lot to cover on determinants. So we've met 2D and 3D determinants before. We've not really talked about what they are. We've used them to translate across volume and integration measures. Here we'll talk a little bit about what they actually are, how to calculate general size determinants. So determinants are always of square matrices, but it could be that you have a 4x4 matrix and you want to take that determinant. So we'll go through how to do that, how it compares to what you know already, and I'll give you a general recipe for calculating them. And then we'll talk about a number of properties of the determinant too. There's quite a few properties. Okay, so firstly, determinants. What actually are they? So we were talking about how a matrix describes a linear transformation or a linear operation on a vector. And so you can think of, for instance, this matrix here acting on just a single vector in the x direction, if this is what this represents, and you will end up with the first column in the vector. So the entries in the first column describe what a single 1, 0, 0 vector is mapped to, and equivalently a 0, 1, 0 would be mapped to the middle column. So we can think of the columns as vectors in their own right, and the determinant, or at least the absolute value of the determinant, is the volume of the parallelepiped formed from the vectors in the columns. So let's break down that statement a little bit. Firstly, what's a parallelepiped? It's an n-dimensional parallelogram. So a parallelogram is just a squashed rectangle. So this is a squashed, I guess, cuboid in 3D space, and you can just imagine n dimensions of that. So the determinant is the volume that you would find inside the parallelepiped if the vectors that define the edges, so here I've got a 3D1, so three vectors, v1, v2, v3, if they were the columns in the matrix. So behind everything, that's what the determinant is actually telling us. It's to do with the volume of the space and the transformation that the matrix is describing. So this is why the Jacobian determinant allows us to transform between volume elements. I'm not going to give you a rigorous sketch, a rigorous description of this, but a non-rigorous little sketch might go as follows. So if we were switching from x, y, and z coordinates to x prime, y prime, z prime, then our little dx's may transform like this, and I guess we can think of these as vectors in their own right. So an amount in the x prime direction is, I guess, a vector in a space, and we can think of that as a small amount in the x direction, so I hats, in the y direction j hats, z direction k hats. And so I guess we could think about trying to calculate the volume of the parallelepiped that's described by the dx, the dy, and the dz prime vectors as its sides. And so we calculate that using the absolute value of the determinant. So if the dx's are if the dx prime is a vector, then we can write its components. So it's I component in the top, j component, k component, and then the same thing for the dy's, the x component, y component, z component, and same thing for the z primes. So we calculate that determinant, and one thing about determinants is we can take common factors out of rows. So this row has a common factor of a dx, this one has a dy, and this one has a dz, which you can take out. And so we effectively just end up with the absolute value of the Jacobian determinant times the dx, dy, dz. So you can, again, this is a non-rigorous sketch, but this is roughly speaking where that all comes from. Okay, so as we've mentioned, matrices are maps or transformations on vectors and vector spaces, and a matrix, and hence the transformation it represents, is invertible if and only if the determinant is 0. Now this is going to be very important for next week. The next week we'll be studying matrix inversion. We'll be inverting a matrix to find its inverse, and you can only do that if its determinant is non-zero. So this if and only if is an equivalence statement. So it means that if it's invertible, its determinant is non-zero. If its determinant is non-zero, it's invertible. And also saying that one of these is false means the other one is false as well. So yes, this is going to be important for next week. And whether or not the determinant vanishes, we'll talk about actually what that means a little bit further down. But roughly speaking, what it's going to mean is that two of these vectors are in the same direction. so the volume vanishes. In which case it doesn't form a proper transformation onto the... it's a many-to-one transformation, and so you can't define an inverse. Okay, so calculating general determinants. Now, we are used to 3D determinants, but we can build up an ND method in analogy with 3D. So let's just consider how we usually do it, and we'll break that down into parts and talk about how those parts need to change for general dimensions. Now, calculating 4D takes a lot longer than 3D usually, and calculating 5D takes a lot longer than 4D, so you're not going to see them too large, and you'll see why it does take kind of exponentially longer. But you may see on an exam a 4D determinant, for instance, and you'll need to know how to calculate it. So this is the standard way that we would calculate a 3D determinant. Let's see, we cross off like this. We calculate the inner determinant and we multiply it by the A1, and then we work across the top row. So then we go like this, multiply A12 by the determinant that you would form there, and then A13 by the determinant you would form here. And we're going to use that methodology, but we can generalize it a little bit. Firstly, it's useful to have some terminology. So these matrices, which you formed from, I guess the first one was formed by ignoring all of this, and it was that. So, and the second one was formed by ignoring all of that, and it was this. Now those are called the minors. And in principle, we could have a minor for any element of the matrix. So we could, for instance, have the A21 minor instead, where we did that. In which case it would be A12, A13, A32, A33, like that. We could have the A22 minor, like this, in which case it'll just have those 4 components, or elements rather. Or we could have this one here, in which case it's going to be that. And so the minor is, it's a determinant, it's not a matrix, but it's the determinant formed from the opposite side of the matrix to the element that the minor is referring to. So that's these M1, the M11, M12, M13. Those are the minors, and you're used to calculating them already, but maybe you didn't realize that you could have a minor for any element, not just the top row in the matrix. Now, secondly, there's the cofactors. So when we were calculating determinants in the standard way, then we had to put a minus sign here. And so the cofactors are going to modify the minors by adding on plus or minus signs in a kind of more general way than this. So they're just going to account for the extra minus signs that we need to include. And the extra minus sign is this factor here. So I guess we could think about, usually we worked along the top row, so we didn't need a minus sign for the first minor. That's because I plus j equals 2. So 1 and 1. Minus 1 to the power of 2 is 1. We did need a minus sign here. We didn't need one here. We would need one there. We don't need one there. We would need one there. We don't need one there. And so you get this flipping backwards and forwards minus signs. And really all that is just this factor here. Okay, so we formed up the minor determinants. We modified them by adding this plus or minus on to create what's called the cofactors. Now, we needed to then sum them up. I guess one way we could sum them is by writing it like this. So the 1 here is just referring to the fact that you're in the top row. Yes, so this is saying sum across the top row of all of these cofactors multiplied by the matrix elements in the top row. Okay, so this is the standard way that we calculate 3D determinants. Now we could modify this though, because we needn't have actually used the top row. We could have used the second row instead, and this method would totally work, right? We could have used the third row too. So we could calculate determinants based on any row you like. We could also switch and use the columns instead of the rows. So you've been used to calculating determinants by counting across the top row. Now you need to understand that you can do this for any row, not just the top, and any column. You may need to be a little bit careful with the minus signs on these cofactors, but otherwise it's perfectly possible to do. And if the matrix has a number of zeros, for instance, in one column, then it's going to be handy to use that column because things are going to vanish a lot quicker. So yes, this method does work for determinants of arbitrary size, and the C's, the cofactors, are really just the possibility of a minus sign multiplied by the minors, and the minors are really just determinants in their own right, but they're one dimension smaller. So it would reduce, this method reduces a 3D determinant into 2D determinants, but it would also work in higher dimensions. So it would reduce 4D into 3D or 5D into 4D, in which case you can kind of just say you had a 10D, you could split it up into 10 9Ds and then split up those each one of those 9D determinants into 9 8D, and you can see why this would take a very long time, but you could program a computer to do this, no problem. And yes, so usually we would only give you questions which involved 4D, or as you see further down, there are some reasons why if you've got a number of different zeros, for instance, then things a 5D determinant might be achievable in a reasonable amount of time as well. Okay, let's just formalize those observations we made and talk about a recipe for calculating an arbitrary size determinant. And I'm going to represent this as a 4x4. So firstly, count along the row or column of your choice, and here the advice is to make life easy by picking the one with the most zeros in. So in this matrix, in this determinant, the column here has 2 zeros in. So we're going to count down the third column because it has 2 zeros. And for each element in that, we're going to form up the corresponding minor determinant, and then we need to multiply it by, let me just add this in, so then we need to multiply by the corresponding matrix element. We need to multiply also by this factor of -1 to the I plus j. And then we'll sum them up. So firstly, we count down the axis, this column, and we'll first get the minor corresponding to this element, which is these elements here. So 4 3 2 in the first row, 1 2 3 in the second row, and 0 1 1 in the final row. And the minors corresponding to these two elements we don't need to care about, because we would multiply those by the corresponding matrix element, which both of those are 0. So the final one we need to care about is the minor of this element. So we remove these, and so the corresponding determinant would be of those elements. So 1 0 1 in the top, 4 3 2 in the second row, and 1 2 3 in the final row. Okay, so those are the minor determinants here and here, and the corresponding matrix elements. So there was a 2 for the first one, so I multiplied by 2 here, and it was a 1 for the final one, so I multiplied by 1. And then this extra factor that we gain for the cofactors. So that's -1 to the power of I plus j for the matrix element you're talking about. So the first matrix element is this, and that is when I equals 1 and j equals 3. So third column, first row. And so I get -1 to the power of 1 plus 3, which is just 1. Then finally, there's this factor here. So -1 to the power of I and j for the bottom one. So we get I equals, let's see, the fourth row, so 4, and j equals 3 again, because it's the same column. So minus 1 to the power of 3 plus 4, which is 7, which is odd, so you'll get a minus 1 factor out of that. And so this is what the method has done. It's taken a 4 by 4 determinant, and it's reduced it down to some 3 by 3 determinants. In principle, you could have 4 of them, but because 2 of these elements vanished, then we reduced it. 2 of them vanished. And so at this point, the determinants are small enough that you would just calculate them by some, we know how to calculate 3 by 3 determinants. We don't need to think about it too hard. And so, yes, I got minus 5 for the first one, 10 for the second one, and so the determinant of the whole thing is this. So we can get minus 10 times subtract 10 is minus 20. Okay, so that's how to calculate arbitrary size determinants. They have to be square, of course. But we can use some of the properties of the determinant to speed us up. And there's quite a few different properties, and we'll talk about them as we go on in later videos and also next week. So firstly, there's a few of these quick identities. Now the T here means transpose. We've not talked about that properly, but all that is what you get if you switch the rows in the columns. So determinant of the transpose is the same as the determinant of the original matrix. The complex conjugate, we can take the complex conjugate before the determinant or after. It doesn't matter. You'll get the same thing. This thing here is the adjoint or the Hermitian conjugate. Again, we'll talk about what that means. Really, it's just the transpose and the conjugate. Determinant of two matrices multiplied together is just the same as the determinants multiplied together. So det of AB equals det of A times det of B. If I multiply a scalar by the matrix, then I'm going to get the scalar to the power of n if the matrix is n by n. So just recall that multiplying a matrix by a scalar is the same as multiplying every element by a scalar. So every single element would get that factor larger. If we have a common factor in any single row or column, then we can factorize that out. So in that case, you will just get that factor on the front rather than that factor to the power of n. You can see if I put lambdas in all of these, then it's the same as doing this 3 times over, so I get lambda cubed here. Now, there's a nice little corollary to this. So a corollary, if you didn't know, is just a small result that follows a more general result. But we can imagine what would happen if we put lambda equals 0 here. Now, that would make the right-hand side vanish. And so if we have a matrix where all of the elements of any row or column vanish, then the determinant vanishes. And I guess a nice thing to imagine there is recall that the determinant's meant to correspond to the volume of a parallelepiped, and this would mean that one of the sides has 0 length of the parallelepiped, so the volume of the parallelepiped is going to vanish too. And if one of the sides of a shape is 0, then its volume is going to be 0. Some more things. Switching any 2 rows or columns flips the sign of a determinant. So if I switch column 1 for column 2, then I need to put an extra minus sign on the determinant. A nice corollary from that is that if they are the same, if there's 2 rows or 2 columns that are the same, then because when I switch them, I should pick up a minus sign, but the matrix itself doesn't actually change, then its determinant must be equal to 0. So, I don't know, if I had 1, 2, 3, 1, 0, 1, 1, 2, 3, then I know that this has to be equal to 0. So det of this equals the negative of the determinant when I switch the first and the third column, because these two are equal, so I could just switch these. But if I switch them, I'm going to get exactly the same matrix back because they are the same. So 1, 0, 1, 1, 2, 3. In which case, we see that the thing equals negative of itself, so it must be equal to 0. So, switched row 1 with row 3. Okay, so there's only a couple left. So this is a pretty useful one, and you can get questions where you can use this to help simplify down very large determinants. So this property says that the determinant is unchanged by adding or subtracting a multiple of any row or column to another. So we can take any row or column and add it on, or any multiple of it on, to another row or column, and that shouldn't change the determinant. So here's an example. So if I've started off with this matrix, or this determinant rather, and in the original matrix, if I add on, let's see, so I've added on 1 times the first row onto the second row. So this would mean a 2 is added to here, making it 3, a 1 is added to there, making it 3, and 2 adds to 0, making it 2, so I get 3, 3, 3 in the middle row. And then, so that determinant should equal the first one. I've also added on here, well, I've subtracted a half of the third column from the first column. So that's going to be subtracting half of 2 from 2, that'll give you 1, subtracting a half of 2 from 3, giving you 2, and subtracting a half of 6 from 3, giving you 0. There. This should be the same determinant. Now, there's a nice little corollary to that, and that is that if any two columns or rows are a constant multiple of each other, then the determinant must vanish. Now, why? Well, because we could then take one column and use it to cancel out the other one, making all of the elements 0. So, for instance, take this determinant here. Now, this vanishes, and the reason I know it vanishes is because column 3 is twice column 2. And so I could subtract 2 lots of column 2 from column 3, and so that would just give you equals det 1, 0, 1, 1, 2, 3, 0, 0, 0. And I know that this vanishes because it has an entire column that vanishes. So yes, if any two rows or columns are a constant multiple of each other, then the determinant vanishes. And you can also think of this as in terms of the volume of the parallelepiped, because that means that the two of the sides are in the same direction. They may not be the same length, but they're in the same direction. And so, yes, you can imagine, or at least try to imagine what this would look like if you modified v1 around so that it was in the same direction as v2. Okay, was that the final one? Okay. Finally, we have 3 properties which are to do with antisymmetric matrices, orthogonal matrices, and unitary matrices, and that we will cover in the next video. So we'll have a video on orthogonal matrices and one on unitary matrices. So I'll see you then.